In this video, we are going to talk about yet another method of root finding, and that method is known as fixed point iteration method. Iteration method. Let us say we have a function for some value of x. This is equal to 0. Now this equation can be written in its equivalent form as x equal to g, where g is another function of x. Now if we say that at some point x equal to r is equal to g at r, then r is known as fixed point, and this is root of the function. We need to understand over here that for multiple values of x, this function may be 0. So it means that it may have more than one root. Now this equation 2, if I want to explain it graphically, let us say that I write down it as y equal to x and y equal to g at x, and I plot a graph between x and y. This is the curve y is equal to g, and there is another curve, that is straight line, passing through the center y equal to x, where these two curves will intersect, that is the root of the function. Now with one example, we will see that how can we write down an equation in the form x equal to g. So let us consider one equation x cube plus 4x square minus 10 equal to 0, and we have to write down this equation in x equal to g form. Now there are multiple ways to do it. One is x equal to x minus x cube minus 4x square plus 10. Another is x equal to square root of 10 minus 4x square by x. Another method is x equal to 1 by 2 root over 10 minus x cube. Then we can also write down it in this form, square root of 10 by 4 plus x, and finally we can write down it in this form as well, x minus x cube plus 4x square minus 10 by 3x square plus 8. Now to operate this particular method, we need to write down xn plus 1 is equal to g at xn. This is what the iteration formula is, or in other words, the iteration proceeds like this. Now let us understand what are these terms. Now xn plus 1 is n plus 1th approximation, xn is nth approximation. So it means we can find out from nth approximation the x plus n plus 1th approximation. So for example, let us consider the initial approximation to be x naught. Then the first approximation x1 can be obtained via this relationship. Similarly, we can obtain another approximation from the previous approximation, and this way we do proceed. Now graphically, if I want to show that how does this method work, then this is the curve and this is curve y equal to g and this is y equal to x. Now if I take any initial approximation, let us say x naught, then I proceed like this, that I draw a vertical line on this y equal to g curve, then a horizontal line on y equal to x curve, then a vertical line on y equal to g curve, and this is my second approximation. Then I draw a horizontal line, a vertical line, and this is my third approximation, and so forth until I reach to the root, which is the intersecting point of y equal to x and y equal to g. So in the given example, if I consider that f is equal to x cube plus 4x square minus 10. So first of all, I need to find out the interval within which the root exists. So let us say x equal to 1. If I look at this one, this comes out to be negative, and at x equal to 2 it comes out to be positive. And we know that if function maps from negative to positive value, then at certain point it will cut the x-axis, and the point where the curve cuts the x-axis, that is the root. So now here in this particular example, we can see that root lies between 1 and 2. Now this is the interval within which the root lies. Now we can write down this particular function in x equal to g form, and for different initial approximations, let us say we take one initial approximation is 1.25 or another one is 0.5, and we proceed and we see that for function x minus 4x square plus 10, the successive approximations diverge. For g2, which is square root of 10 minus 4x square by x, once again we see that the successive approximations diverge. For g3, however, we see which is 1 by 2 root over 10 minus x cube, the successive approximations do converge. Same happens for g4 and g5. If I change the initial approximation to 0.5, still I get for g1 and g2 that the successive approximations diverge, while for g3, g4 and g5 I see that the successive approximations converge. If I take initial approximation as 7 and I have calculated it for function g5, and I see that for first 4 values, that is initial value and the next 3 approximations, the successive approximations monotonically go towards the root. On the other hand, for these values, I see that the successive approximations oscillate about the root, and as we can see that these two values are same up to third decimal place, so the root correct to 3 decimal places is 1.365. Graphically, if I show it, I see that if I start with some initial approximation, then I can see that I draw a vertical line on the graph, on the curve, and then a horizontal line from that curve to the straight line, and then vertical line, it doesn't cuts this curve. It means that the successive approximations will diverge. The same thing I can see over here, that here also the successive approximations diverge. On the other hand, for G3 function, if I start with some initial approximation, then I see that these successive approximations finally do converge to the given root. Same is for G4 and the same is for G5. However, what do I see over here, that when the slope is positive, G prime is positive, then if I start with some initial value, I can find out that the successive approximations monotonically move towards the root, but when the slope of the curve becomes negative, the successive approximation starts oscillating about the root. So this is very important thing which we will remember. Now, why in some cases, that is why for some G's the successive approximations diverge, while for some the successive approximations converge. So what is the reason behind it? So that is what we are going to talk about. Now, in order to successive approximations to converge, let us find out that condition. So let us say that G and G prime, that is derivative of G, both are continuous in some interval. That interval, let us say, is AB. So if this particular condition is satisfied, then the successive approximations will converge. On the other hand, if this condition is satisfied, that is the derivative of g is greater than 1, the successive approximations will diverge. And what those successive approximations are? Xn plus 1 equal to g at xn. So it means that unless this condition is satisfied, the successive approximations are not going to converge. Let us see this with our example. So if I take for the same equation for different forms of x equal to g, I take the derivative. That derivative for the first function will be given by my 1 minus 3x square minus 8x, and so g1 prime at, let us say, 1.5, as the interval is 1 to, this is 17.75 and this is greater than 1. Hence, as we saw that the successive approximations did diverge. For another form g2 prime, we took the derivative of the function g2, and this is given by minus 2x square minus 5 by x to the power 3 by 2 root over 10 minus 4x square. And so at x equal to 1.5, this g2 prime at 1.5 is greater than 1. Remember, we are taking here the absolute value. So this comes out to be greater than 1. So we are taking here the absolute value. That is what we need to remember always. Then for g3, it is minus 3 by 4 x square by square root of 10 minus x cube, and at x equal to 1.5, g3 prime at 1.5, the absolute value is less than 1. For g4 prime, the value is minus root over 10 by 2 x plus 4 to the power minus 3 by 2, and at x equal to 1.5, this is also less than 1. And for the form E, g5 prime, the derivative is 1 minus 3 x to the power 4 plus 24x square plus 124x divided by 3x square plus 8 whole square. At x equal to 1.5, this g5 prime at x, its absolute value is less than 1. So it means that the absolute value of derivative of g must be less than 1 for the successive approximations to converge. In addition to this, if g prime is negative, that is g prime is less than 0, then successive approximations will oscillate about the root. On the other hand, if g prime is positive, then the successive approximations shall approach to the root monotonically. So remember this point, that if g prime absolute value is less than 1, but g prime not absolute value, only g prime, that is derivative of g is negative or slope of g is negative, then the successive approximations will oscillate about the root. And if g prime is positive, that is derivative of g is positive, or in other words slope of g is positive, then the successive approximations shall approach to the root monotonically. Now what if that this g prime is equal to 0? If it is equal to 0, then the convergence will be very fast. This is what it will be. So from this it comes out that if the value of g prime is small, then the convergence to the root will be fast. On the other hand, if g prime absolute value is equal to 1, then convergence is not guaranteed, and if at all the convergence will happen, it will happen painfully slowly. So if this condition is satisfied, then the convergence is not guaranteed, it may diverge also. On the other hand, if the convergence do happen, it will happen very slowly. This is what in the first part of this fixed point iteration method. In the next video we shall talk that why this condition, that is absolute value of derivative of g, must be less than 1 in order to successive approximations to converge to the root.